Hey everyone, and welcome to another Explainer. If you are a ninth grader at St. Paul American School Clark, you are exactly where you need to be. I am absolutely thrilled to have you here today. So, get ready to focus because we're tackling a really foundational piece of your mathematical journey. The exact production title for today's lesson is G9, Geometry, Unit 2, Lesson 5, Rotations and Rotational Symmetry. Whether you're aiming to absolutely crush your next exam, or you just kind of want to understand the hidden geometry governing the physical world around you, you are in the right place. We are going to break down these concepts step by step. Let's get started.
Okay, let's dive into our highly structured agenda for today. First up, our objective. Second, the blueprint, where we'll cover the core concepts. Third, an example comparing rectangles and squares. Fourth, a misconception check. Fifth, a quick formative check, and finally, we'll wrap it all up with a recap.
Section 1. Objective. Defining the learning goal. So here is our objective for this explainer. We are going to master rotations, rotational symmetry, and the exact parameters required to transform geometric shapes. Notice that we are focusing strictly on rotations today. We want to know exactly how a figure turns, what rules it completely obeys, and how we can mathematically describe a shape that looks totally unchanged even after we've spun it around.
Section 2. The blueprint. Concepts. Let's unpack rotations.
All right, I need you to lock in right now because we're about to learn the non-negotiable definitions that are going to serve as the foundation for the rest of this unit. A rotation is a geometric, rigid transformation that involves rotating a figure a certain number of degrees about a fixed point. Think of a point, and just imagine a shape moving along a circular path around that exact point. Now, the absolute key here is that to rotate a shape, you move each point on the shape the given number of degrees around that circle. And critically, make sure each new point is the exact same distance from the point of rotation as the corresponding original point. It doesn't shrink, it doesn't grow, that distance remains identical.
To execute a rotation properly, you absolutely need these three pieces of information. I like to call this the rule of three for rotations. First, the center of rotation. This is your fixed point, the center of the circle passing through corresponding points. Second, the direction of rotation. Are you going clockwise, like the hands on a wall clock, or counterclockwise? And third, the degree of rotation. This tells you exactly how much you're actually turning. Remember, a full, complete circle is 360 degrees. Without all three of these parameters, your geometric transformation is simply incomplete.
Now, what's really interesting about this next slide is this fascinating concept of rotational symmetry. A shape has symmetry if it can be indistinguishable from its transformed image. So specifically, a shape has rotational symmetry if there exists a rotation of less than 360 degrees that carries the shape right onto itself. Imagine taking a shape, pinning it to the wall straight through its center, giving it a spin, and stopping before you make a full circle. If the shape looks like it literally never even moved, if it perfectly overlaps its original footprint, it has rotational symmetry.
Because mathematicians love precision, we have three different ways to name and quantify this rotational symmetry. First is order, which is really just the number of times you can rotate the figure so that it looks exactly the same before you get all the way back to your starting point. Second is fraction of a turn. If a shape looks identical halfway through a full spin, well, it has 1/2 turn symmetry. If it looks identical a third of the way, it's 1/3 turn symmetry. Finally, angle. This is the smallest angle the figure can be rotated to coincide with itself. So order, fraction, and angle are truly just three different languages expressing the exact same symmetrical property.
Moving on to Section 3. Example, rectangles and squares. Bringing concepts to life.
Let's see how these three naming conventions work on actual ninth grade geometry shapes. We're going to compare two of the most common quadrilaterals, the rectangle and the square. And this brilliantly illustrates the differences. Look at the rectangle. You can rotate it 180 degrees, a half turn, about its center, and it will look exactly the same. So it has an order of 2. Now consider the square. Because the square has 4 equal sides and 4 equal 90-degree angles, you only have to turn it a quarter of the way around, so 90 degrees, for it to look totally identical to its starting position. Therefore, the square has a much higher order of symmetry. It has an order of 4. Literally every 90 degrees, it perfectly coincides with itself.
Section 4. Misconception check. Direction of degrees. Pay very close attention here because this is where a lot of brilliant students lose points. Really think about this for a second. If a test asks you to rotate a geometric shape by a positive degree, which way does it actually turn? Clockwise or counterclockwise?
Here is the golden rule you absolutely must memorize.
If the degrees are positive, the rotation is performed counterclockwise. If the degree measure is negative, the rotation is clockwise. Positive degrees go counterclockwise. I know, it feels incredibly counterintuitive. You'd naturally guess that positive means the same direction a clock moves, right? But in geometry, it's the exact opposite. Burn this rule into your memory right now. Positive is counterclockwise. All right, Section 5, Formative Check, Testing Your Knowledge. Let's ensure you're actively grasping these concepts. Read this challenge question carefully. How many angles of rotation cause a square to be carried onto itself? Think back to that example we just covered. I'll give you a second.
The answer is 4. Did you get it right? Rotations of 90 degrees, 180 degrees, and 270 degrees in either direction will all cause the square to be carried onto itself. And of course, the 360-degree full rotation brings it right back to the start. Because it has quarter-turn rotational symmetry, it has an order of 4. If you got that, you are in fantastic shape for this unit.
Section 6. Recap, cementing the knowledge.
We are nearing the finish line, so it's time for a rapid-fire summary to synthesize this data so it actually stays in your long-term memory. So, the crucial point is summarized right here in our core takeaways. Number 1. Rotations absolutely require 3 parameters: a center of rotation, a direction, and a specific degree. Number 2. Never forget that counterintuitive rule that positive degrees rotate counterclockwise. And number 3, when a shape can be rotated less than 360 degrees and look perfectly unchanged, we name that rotational symmetry by its order, its fraction of a turn, or its angle.
I want to leave you with a provocative thought as we wrap up. Look around the room you're sitting in right now. Seriously, look at the ceiling fan, look at the hubcaps on the cars outside, look at the bottom of your coffee mug. What everyday objects hide rotational symmetry of order 3 or more? Geometry isn't just something on a screen, it's literally the blueprint of the physical world around you. Thank you so much for joining me on this explainer. Keep looking for the math in the real world, and I will see you on the next one.